So, in continuation of the propyl gallate synthesis and it is very important to have antioxidants in for the many processes, including the DNA not to cause DNA damage. So, antioxidant consumption is very important, and the food are rich in antioxidants are various, including the various vegetables and fruits and even the I would say the type of so even the pomegranate juices. And what type of compounds are antioxidants? So, basically the phenolic compounds, okay. So, phenolic compounds as well as the phenolic compounds, and this one are antioxidants, okay. And if you could see that here in the pomegranate extract, you will find out there are juice extract, you find various phenolic compound which has the antioxidant properties. And in this case, we would like to synthesize propyl gallate, which is one of the synthetic antioxidants. It also used as a food additive. So, obviously, you want to have antioxidant in the processed food as well as various to improve their shelf life, and due to the various oxidative processes it will get decomposed. To avoid that, so you want to add food additives. This one of the food additive is propyl gallate, and then as the name suggests, the propyl gallate is an ester which could be synthesized from gallic acid and the reaction with propanol. The reagents needed for the synthesis of propyl gallate are gallic acid, the name is written here very clearly, 3,4,5 trihydroxybenzoic acid, and propanol of course, and DPPH to measure the antioxidant activity of gallic acid, propyl gallate. Trolax is the control compound for the DPPH activity, and methanol, ethanol for the solubilization of DPPH and Trolax, and propanol to react with the gallic acid to form the propyl gallate, sulfuric acid to catalyze the reaction between gallic acid and the propanol, and sodium hydrogen carbonate basically to neutralize the sulfuric acid used while extracting the propyl gallate, sodium sulphate, anhydrous sodium sulphate to dry the organic medium, and dichloromethane, diethyl ether to extract these things. And the progress of the reaction can be monitored using a thin layer chromatography, and in a pre-coated silica gel with the thickness of 0.2 mm with the fluorescent indicator at 254 nanometer. And you can see here how the procedure is written very clearly. You see here the what is that, gallic acid, okay. Gallic acid is this one, and this is dissolved in propanol and a little bit of acid, and so the procedure is as follows. You need to dissolve basically the gallic acid in 50 ml of propanol, and catalytic amount, that is only a 0.5 ml of sulfuric acid was added while swirling to the reaction, and the round bottom flask is attached to the reflux contention, and basically you heat the reaction mixture at the reflux condition for nearly about 1 hour and 30 minutes or about 90 minutes. After cooling to the room temperature, and you need to evaporate the solvent partially at the reduced pressure, and why we are adding, we are removing the most of the propanol, that is to improve the solubility of propyl gallate with the organic mixture, because if you have a more N-propanol, that it tend to reduces the yield of the reaction. So, if you remove the N-propanol, so the extraction efficiency with the diethyl ether increases. That is the reason you are removing the most of the N-propanol to improve the solubility of propyl gallate with diethyl ether, and the aqueous medium is extracted with the 3 times diethyl ether, and you separate using a separating funnel, and the combined organic phases with washed with 10% of sodium bicarbonate. That is to remove the residual sulfuric acid may be present in the reaction mixture, and after evaporation of diethyl ether, you will find the crude product, which could be crystallized from diethyl ether and petroleum ether actually. Okay. And the TLC we have talked about in the last few lectures. The TLC has to be monitored, as we talked about before. You need to have both of them. It is easy to monitor. The propyl gallate is more acidic, more polar when compared with the gallic acid is more polar when compared with the propyl gallate. Propyl gallate will be non-polar, and of course, the propanol will not be, it's only a solvent being used. So, you may not have to use the propanol as one of the this thing. So, normally the TLC for this can be done as follows. So, you have only the 3 spots, okay, 3 spots, and you have a mass medium, and you put 3 spots. One is, so 1, 2, 3. The first spot, put only the gallic acid, and the second spot, gallic acid plus reaction mixture, third spot only the reaction mixture. So, now since we are putting, if gallic acid is done in the basically the dichloromethane ethanol 8:2 the ratio. So, 20% of methanol in dichloromethane, and gallic acid will be little bit more polar when compared with the gallic, so it may be coming here. So, this is a reaction mixture. So, you will have both, if it is incomplete, you will have both gallic acid and propyl gallate, okay, and this is only the propyl gallate. When the reaction is complete, you do not see any spot of gallic acid at reaction mixture, and the second spot will have reaction mixture, and this one. With that, you will be able to complete the, you can ascertain the completion of the reaction. So, it will tell very clearly. So, what is the completion of the reaction is done or not. Okay. So, of each group should be delivering to the instructor or the TAS. Now, we have synthesized basically the propyl gallate, and how do you check the purity of it, and so what is that you are going to see it. So, you are going to see the, I am just writing the structure of gallic acid and propyl gallate. The NMR here is shown here only for the aliphatic region, not for the aromatic region. The reason I will explain in this slide. So, you have propanol, you have propanol and H plus, you lead to the formation of propyl gallate. So, both reactant and the product, the aromatic region remains constant. Aromatic region remains constant. So, there is no need to worry about what is in the aromatic region. Only the aliphatic region, if it is the OH is there or not, we can find out. That is why you see it here. You see a peak at around 4.2 delta. 4.2 delta as a triplet, okay, and this about 2.5 is not integrated. This for the solvent peak DMSO, and this is DMSO water, which is about 3.6 is DMSO water, and or it could be also for the, I think it is only DMSO water, and you will see for 2 protons at 1.7 and about 1 delta you see 3 protons. So, this values denotes the integration number of protons. So, this is a triplet, this is a triplet, okay, comes from this CH2. So, this we can say CH2A, CH2B and CH3C. Okay. So, this one attached to the O, CO. Normally, the oxygen attached hydrogens will come around 3.6 delta in the NMR. Since it is also attached to the carbonyl, it has much more downfield shift, and it also indicates that this hydrogen flanked by another 2 hydrogens, because n plus 1 rule in NMR, you get the triplet for this hydrogen. Okay. You see the triplet at 3.2 delta, this shows that. So, this hydrogens CH2 are flanked by 5 hydrogens, this side 3 and this side 2, this flanked by 5 hydrogens. Totally you get 6 peaks. That is what you see here for the sextet, say 1, 2, 3, 4, 5, 6. So, for this one you see the sextet for this B hydrogen. Of course, if you take this methyl, it also adjacent to a 1 CH2, you get a triplet. So, that is what you see here. This is for the CH3, this is for the CH2, this is for the OCH2. So, please understand this, the characterization of the compound by the NMR, so that the exams and everything will be able to explain what are the peaks corresponds to which. And this is the C13 NMR, okay, C13 NMR. This is C13 NMR. So, I am drawing only the structure of propyl gallate. See, look at the number of carbons here. You have 1, this is 6, 7, 8, 9, 10. There are 10 carbons are present in the propyl gallate. So, you see the number of things are present here. You see about 1, 2, 3, 4, 5, 6, 7, 8. So, you do not see exactly the same number of carbons for this one. You can say that there is a kind of symmetry goes through that, and this carbon and this carbon may come at the same position about this carbon and this carbon. Okay. So, this what the intensity of this one also denotes a particular one, and this one and this one may come around here, and the carbonyl this comes around 165. The chemical value of this carbonyl, this comes around 168 to 169 delta ppm. So, anything carbonyl compound, it comes beyond 160. So, please remember, as similar to the NMR here, you can easily say that this corresponds to the OCH2, this corresponds to CH2, this corresponds to the CH3. So, like that we will be able to basically assign all the hydrogens, all the carbon for the in the C13 NMR for a particular product. So, now we have synthesized, we have characterized. The next agenda is to find out, can we do the antioxidant activity of the propyl gallate. So, antioxidant of propyl gallate comes from these phenolic compounds. So, basically the ability of these phenolic compounds to donate the hydrogens is able to quench the radical or reactive oxygen species present or in the food additives, foods or in the biological systems. How do you measure the antioxidant activity? So, there are 2-3 methods are there. That is one of the method is oxygen radical absorbance capacity, and another one is a trap assay. There is a ferric reducing antioxidant power, and the cupric assay, the cupric ions reducing anything. And what we are going to do is a little simple one, that is a TPPH assay actually. Okay. So TPPH nothing but there is a diphenyl 1-picaryl hydrazine, that is the compound, diphenyl 1-picaryl hydrazine, that is what the compound is, and that is the assay we are planning to do it for this one. And how the assay works? The antioxidants react to TPPH, and TPPH is a very stable radical. If you see the structure, you will be able to appreciate why it is a very free radical, and it has, because of the radical structure, it has absorbed the different wavelength, and this after the reacting to the antioxidant, it is reduces the TPPH. As a consequence, there is a decreased TPPH radical to the TPPH H form. So, instead of being a radical, it formed to the TPPH H form. So, the degree of discoloration, because of radical is no more, the degree of discoloration indicates the scavenging potential of the antioxidant compound or any extract in terms of hydrogen donating ability. So, in this case, basically the TPPH is a radical, the radical is being quenched by the donation of hydrogens from the phenolic compounds present in the, again, it could be a extract or it could be the propyl gallate or any one of it. So, the simple reaction can between the TPPH and the antioxidant can be written as follows. You can see the TPPH alone, you have only the purple color. Okay. So, upon reacting with the antioxidant, donation of hydrogen from this one, it leads to the formation of TPPH and hydrogen, which is in yellow color, and with the change in the coloration, you will be able to get the activity of the compound. How the scavenging assay? This is basically a diphenyl hydrazine, the free radical, okay, TPPH, and you see the nitrogen is present because of the picaryl group present, it is stabilized and it absorbs out pink color. And when you go for the antioxidant property, it donates the hydrogen, lead to the formation of the radical, and it creates a diphenyl picaryl hydrogen, which is a non-radical actually. So, this is the reaction between the TPPH, and measurement of the OD at 550 nanometer need to be done. What is the procedure for TPPH assay? And it is again the same manner, is to have pictorial representation in a better way. You see that TPPH, which is the oxidized form, and DPPH, which is in a reduced form, that is yellow color, that is the oxidized form, reduced form. So, that is in purple, that is in yellow color. So, what are the chemicals required? And you require the TPPH, that is a 1,2,2-diphenyl picaryl hydroxyl hydrate, that is the one. Methanol, you need analytical grade, UV visible spectrophotometer and micropipette. Of course, you need to have also either propyl gallate, which is our interest, okay, and the control compound, okay, that also for measurement of this one. How the experiment was done? And experiment was done with the 0.1 millimolar TPPH was prepared in methanol, and 4.9 ml of TPPH, the 0.1 millimolar solution was mixed with 0.1 ml of sample solution, the propyl gallate, and with the standard cell solution separately and in triplicates, always, because you do not want to have error in the measurement and everything. So, it is done in triplicate or even quadruplicate you can do, and the solution was taken vigorously, and then the allowed to stand in the dark, because of the radical thing, you do not have any background reaction by the light. So, it is dark for 30 minutes. The OD was measured at 570 nanometer using UV visible spectrophotometer, and methanol 0.1 ml along with the Trolax is used as the with the DPPH solution as a control, as a blank, and as a control you have TPPH, instead of TPPH, Trolax, which is a positive control, was used. And this is how to make that solution. So, 39.4 milligram of TPPH was dissolved to make the 1.1 millimolar in 1 liter of analytical grade methanol, or even like 3.9 milligram of thing will be dissolved in the 100 ml of analytical grade methanol, and you can always do the serial dilution to the various level by calculating the N1 into V1 and M2 into V2 formula. And you will see the absorbance value for the various ones. You see what is the absorbance value, the straight line has to be drawn, and you will see what is the control, what is the extract S. This is for the different compounds, and for the how do you measure the anti-radical this thing, procedure inhibition, you have a control and sample divided by control, and also you will find the antioxidant activity index, that is the AAI. Okay, it is measured by the final concentration of DPI in microgram per ml and IC50 about microgram per ml. TPPH you find out gallic acid of EC50 of about 10.4 micromolar, AA is about 27.54, propyl gallate is 6.7, and Trolax is this one. So, it is about 34.1 and 6.61 for the this our control compound. So, this has a better what you call antioxidant values, and in inference what we have done is the propyl gallate was synthesized and characterized, and antioxidant activity of propyl gallate was measured and demonstrated. And you please, the reference for this experiment is again ACS Journal of Chemical Education, Journal of Chemical Education, Journal of Chemical Education. The year was 2011, the year was 2012. Okay, the year was 2012. The volume number was 89, the page number was 130 to 133, 130 to 133. Okay. So, the article can be accessed from pubs.acs.org, pubs.acs.org, and institute has this access. So, if you don't have to, if you are unable to access, please let the TA know, we will send you that. And also please go through the supporting information for every experiment we are doing. Please go through the supporting information in complete, in toto. Read through the supporting information completely. Okay. Read through the supporting information. So, that is also you can access in the pubs.acs.org. Okay. So, please go through everything, and we will ask most of it from the supporting information as well as what are the experiment we are doing it in the classes actually. Okay. Let me stop here, and we will continue for the next lecture.
Weigh 0.5 gram of gallic acid and transferred to a round bottom flask. Add 50 milliliters of N-propanol to the same round bottom flask and start stirring. Add 0.5 milliliters of sulfuric acid with swirling to mix the solution. Attach the RB to a reflux condenser and reflux the reaction mixture for 1.5 hours. Monitor the reaction using TLC. Once the reaction is completed, cool the reaction mixture, add 15 milliliters of 10% sodium bicarbonate and extract the mixture with ethyl acetate. Extract the organic phase and wash with distilled water. Separate the organic layer and dry it over sodium sulfate. Concentrated the organic layer in rotary evaporator and white solids of propyl gallate is obtained. Freshly prepare 0.01 mg per ml DPPH solution in methanol. Prepare individual solutions of propyl gallate and gallic acid at concentrations ranging from 0.01 to 0.16 mg per ml in methanol. Place 0.1 ml of the sample solution and 3.9 ml of DPPH solution in vials and incubate covered at room temperature for 30 minutes. Methanol alone is used as control. Measure the absorbance of the control and each sample at 490 nanometers in UV visible spectrophotometer.